Hi, I'm Roland Kuhn. I'm one of the founders and the CTO of Actyx. And in this video, I will show you the contributions we are making to the TaRDIS project. I'll demonstrate this on a simplified problem setting. This problem setting is we have a set of plants. Every computer will run one plant. And these plants are in need of watering, as real plants do. We have a fleet of robots. Every computer will also run one robot. And these robots will see the requests of watering from the plants and will collaboratively sort them out, deliver water to the plants. The important thing to note here is that this is everything that there is. There is no other participants, no managers, no databases, no central control. This is a peer-to-peer system consisting just of the robots and the plants. The software will all run in the browser and will communicate using the Actyx middleware, but I'll get to that. The interesting thing about this problem setting is that logistics is one of the most prominent use cases in many industry verticals. If you have a machine that needs material to produce something, then you need to have a logistics fleet, usually consisting of workers, but more and more it's also AGVs. That service this request, so that fetch something from a warehouse, deliver it to the machine, so that the machining can happen. So we have this simplified case here just to make it easier to demonstrate. The first step when working with swarm protocols is to note down what the protocol is. And for this, we have seen that our customers prefer a visual representation, something like this. So people tend to think in these kind of state machines where we have the arrows representing events that happen in the system and the boxes that represent the states that the workflow can be in. We start from the left-hand side. The request is made, and the yellow underline is that this is done by the plant. Now, the green underline under the offer, for example, shows that when we are in the requested state, offers can be made by logistics robots to service this request. And this is a self loop, so an offer does not change the state. Many requests can be made. At some point, either a robot decides that the whole process has failed, or the plant can assign one of the robots to service this request. At that point, we are in the assigned state. Again, failure can happen. This is a real system, so we have a fail to transition into the failed state. The next thing that happens is that after the plant has assigned the robot needs to accept that it now takes on this job. So the fail to is for the case where the robot does not accept in time. Now, after accepting, we expect the robot to perform the job. And for that, it will be in the moving state. It will emit move events, a series of them, as it moves toward where the plant is. And then it will emit the finish event once it has reached its destination, and then the plant will know that it has been watered. Of course, the robot can fail, batteries die, whatever. So the fail 3 error condition also brings us to the failed state. Now, with this diagram, with this design of the protocol or the workflow, we need to go towards making a program out of it. The first step is that we need to transcribe this diagram into a JSON data structure. One improvement that is worked on in the TaRDIS project is a graphical workflow editor tool that will allow you to directly edit these things and get the JSON in your program updated as you edit the graphics, but we don't have that yet. The shape of this protocol type looks a bit like what you see here on the screen. You see we start in the initial state, which was not on the diagram. It was the start of the left arrow. And then we go to the requested state by way of the plant performing the request command, which emits a request event. Now there is one line for each arrow in the diagram, and the states are the source and the target here are named implicitly. This constructs the whole graph that you have seen in the slide before. So once we have designed this swarm protocol, we need to implement it. Now, this swarm protocol is the global view that you see when you look at the system from above, knowing everything, godlike, if you will. Now we need to write down the local workflows to run the actual agents. So one for the plants and one for the robots. For this, we use the Actyx machine runner TypeScript library, which offers a DSL to perform various tasks. The first one is to declare the event types. The event types are declared together with the protocol because they are shared between the plant and the robot. This is the way these two communicate, so they need to speak the same language. We use a TypeScript library called Zod that allows constructing, validating descriptions of the payload of the event data, but this is a detail. The most important part is that we use this here, machine event .design, which is an API offered by the machine runner to create the request event type that carries this particular request payload. So we have lots of event types here, each one corresponding to one of the arrows in the protocol. In the end, we tie this together. So swarm protocol make takes a name for the protocol. We call it the watering protocol, and the set of all events. This allows us to check whether we use only allowed events in what is to follow. So we have declared the event types. Now we declare the workflow states, and in each state we need to define for that role, so whether it's a plant or a robot, the active commands that they can execute. Let's look at the robot for this. This is the robot. We take this watering protocol that you've just seen and say make machine robot. So we start a factory for the robot role in this protocol. This robot machine is then used to design various states. The initial state is empty, so that it doesn't have any knowledge, it doesn't have any payload data, so this is very easy to create. The next one is more interesting. The requested state has some knowledge. It knows the plant ID, which needs water, it knows the plant position, so where the plant is, and it knows the robots that have submitted their bids to perform this task. It also offers two commands. So this robot array here needs to get its information from somewhere, and this comes from the offer command. The robot has the power to say, I offer to do this. For that, it needs to supply this offer payload, which includes its own position and its name, the robot ID. And then there's also as you've seen there was this other arrow to fail, so there is a command to emit that fail event. This one just has the robot ID, which performed the failure. You can see that this goes on for the other states as well. Now we have declared the workflow states with their commands. The last one we need to do to complete this state machine is to define the event-driven state transitions. So we can look at that here. It's these React clauses. So the robot initial state is the one that we defined above. And when you're in this state, you can react to the request event, and that brings you to the requested state. Now, I told you that the states, most of them have some knowledge in them. They have a state payload that needs to be computed. So we have the old payload that was previously known, which is in this context. And in this case, that context is empty because the initial state didn't know anything. And then we have the event payload, so the contents of this request event. Now we take out the position and the plant ID here and update the current state. Now requested can process the offer event, staying in the requested state, just pushing the new robot ID into the robots array that has made offers to perform this task, and so on. So now we have created this state machine, which has, so we have codified the behavior. Now, the local workflow is now written down in TypeScript code. One very important thing is the designers, so the experts on production in the factory, for example, are not comfortable reading that code, and they cannot easily spot errors in that code, but they can easily spot errors in the diagram. So what we need to do is we need to check that the diagram makes sense from a program perspective, and also that the code implements the diagram faithfully. For that, we have TaRDIS verification tools. The first one is we extract the structure of the protocol using facilities of the machine runner library. This gives another JSON data object. And then we use the Actyx machine check library to verify that this implemented state machine faithfully implements the protocol that we want. This is illustrated here. If you look at here, robot machine is what we just defined.
Alex, ich zeichne gerade was auf hier.
Robot machine is the state machine that we just defined, which offers a function create JSON for analysis, to which you give the initial state, and then it will traverse the state machine to come up with this data structure. We do the same thing for the plant machine. From that, we know which event types are consumed by either of those. These are the subscriptions. And then we have two things that we can do. First, we can check the swarm protocol, which is this protocol that we defined here. The protocol, we check it with these subscriptions whether it is well formed. This means that all the participants listen to all the important events so that they stay on the same page where we are in the workflow. The technical term for this is we want to achieve eventual consensus, and this checks whether any execution in a swarm of this protocol achieves eventual consensus. The second one is that we check the protocol with these subscriptions for the robot role. So we make we project out what the robot is supposed to do in this protocol, and we compare it to the robot machine here that we got the JSON for analysis from. Now, if we run this using npm test, we see an error message. So if you do something wrong, you will get something like this. It says missing transition, fail 3, fail 3. So command fail 3, event fail 3, in state moving for the robot, because we tested the robot. So checking here, we can indeed see that I commented out this command. If I remove the comment and run this again, then now the test passes. We have successfully verified that this code correctly implements the robot role. The last part is the execution. We don't just want to declare these protocols and workflows, we also want to actually run them and use them in applications. The first thing to note is that it is the application that decides which of the local workflows to instantiate. In this case, each watering request is a workflow and has an identifier. So we need to figure out which ones to wake up and check the state of. Then the machine runner provides functionality to run each of these instances that we want. This happens in the background and is controlled by the Actyx middleware. So this is a TaRDIS internal service, as we call it, because the execution of the state machine itself is outside of the control of the application code. This allows us to make sure that it runs correctly without the programmer having any possibility to make it behave incorrectly. Events are emitted whenever commands are executed on these machines, and the Actyx middleware disseminates them throughout the swarm so that they are eventually received by everyone who needs to have them. And then the state machine updates its state, and this updated state is notified to the application code so that it can act accordingly. How does this look in code? Let's look at the plant example here. This is the request water function. It has more details because this is a fully running demonstrator. The important call is here. So create machine runner is the API from the Actyx machine runner library. It needs a connection to the Actyx middleware. It needs the protocol tags, so how to find the events that belong to this protocol instance, then the initial state for the plant in this case, and all the knowledge that we have in the initial stage, which was nothing in this case. Then this is used, as you can see here, it is consumed in a for-await loop. For-await is the language construct of TypeScript that is most suitable for this purpose. It will use this as a generator. So whenever there's a new state update that happened due to locally emitted events or to events that came in from the network, we get a new iteration of this loop with a new state value. And this state can then be inspected. So if it is the initial state, then we run the request and so on and so on. So just to conclude the overview part, the features we had in Actyx before TaRDIS. So Actyx is not a TaRDIS new product. We had it before. It will be substantially improved as part of TaRDIS. So what it did before that even is event replication in the whole swarm, with every event stored permanently on all nodes. It has these state machines for modeling, interpreting the resulting event log. It has some initial work on the well-formedness constraints for these protocols. The new features that we get with TaRDIS is we implemented already ephemeral event streams so that you can forget old events and keep swarm storage requirements bounded so that you don't need infinite disks to run systems for a long time. This can be configured by the administrator of the swarm. Then there's an ongoing effort, as I already told you, to have this graphical swarm protocol editor, which will be very beneficial to the domain experts. And then there is also ongoing efforts to make the protocol checks that I briefly spoke about regarding eventual consensus more precise and more expressive. So currently you need to subscribe to too many events, more than necessary, and we try to get that better and make it more flexible so that it can cover more use cases. Now, this would not be a demo without anything running, so let's run things. This runs an Actyx node, and it serves this application that has been built, and I will open it in an incognito browser tab here. So you see, this is not any published UI, it just shows what's going on. This created one plant and one robot. The plant, you can see, has a watering level that is dropping, and the plant is at this position and the robot is at that position. When the water level reaches 50, then the plant will ask to be watered. This has happened now with the mission ID, and now the robot is moving towards the plant. This might be a close case, but I think it will make it. So watering has happened. Water level was up to 100% and is now dropping again. It will be watered later. So this is just running on one machine, so to speak. Let's use another browser. Here, now we see we have two plants and two robots. The old one here is the plant that has 50%, which was watered now by the robot that was already there. And the other one has yet to reach 50% to ask for water from the other robot. You can see both applications show the same state. Everything is synchronized across the swarm. Thank you. This concludes the demonstration.